Hi, welcome to my channel, JaberTime. I'm gonna go over today the dot product. I have two formulas on the screen, as you could see. The first one is when you do the dot product by multiplying the components of the vectors. And the second one is when you multiply the magnitudes times the cosine, the angle in between. This is just like a quick summary of what I'm gonna go over. Next video is going to be the cross product. This is my fourth video recording today. I recorded 3 for college algebra, and this is for calculus 3. I want to take a break, then I'll come back, write the notes for the cross product, and record by tonight. The dot product is going to be a scalar product, a constant. The cross product coming later on after this section will be a vector product. Okay, let's get into it and be practical to the best that I can and save you some time from going over introductions and so on. The dot product. It's so simple to the point that you just multiply the components of the vectors, as you could see, and add them up. So a dot b, if you are given two vectors a and b, you just multiply a sub 1 times b sub 1, and you multiply a sub 2 times b sub 2, add them up, and you're done. What about if it's in 3 dimension? Same idea. a1 b1, a2 b2, a3 b3, and add them up. We call the dot product a scalar product to distinguish between it and the cross product, and sometimes it's called inner product. So the dot product or the inner product are the same. Let's practice with numbers. This is my A, this is my B. This is my A1 and this is my A2, B1 and B2. 2 times 3, 4 times -1. Do the math and the answer is 2. How about if it's not written in this format? We need to get used to both formats. Vectors are even written with the less than, greater than, if you want to call it that symbol, or IJK. IJK. Whenever I say IJK, I think about IDK. This is 1I, 2J, -3K. This has no I, just J and K. And to multiply it, because it doesn't have an I, you're going to multiply 1i, 1, which is 1, times 0, as you could see. You're going to multiply 2 times 2, and you're going to multiply -3 times -1. The answer is 7. Some properties of the dot product. They're all simple to memorize, and it's good to have them or know that there are there when you use and simplify problems or verify things. A dot A, a vector dot itself, will give you the magnitude of A being squared. A dot, the sum of B and C, all these are vectors, will be the same as A dot B and A dot C being added. A dot B will be the same as B dot A. Well, this one is so clear to talk about because I don't want to keep talking about these ones. There's no need, trust me. Take a look at this. If you switch these two, that's A times dot B, and if you write it the other way around as B dot A, you're going to multiply 3 times 2. So here you're going to say 3 times 2 instead of 2 times 3. And here you're going to end up saying -1 times 4. Same thing. So you could say that the dot product is commutative. Here you could say that we have a distribution law of the dot product over the addition of vectors. Okay, on this one here, C is a scalar. Usually books, when they write letter A and letter B and letter C, when they refer to letter C as a scalar, they change the font to a smaller one and lighter. Well, with my markers, I can't make it lighter. or smaller. I'm trying, as you can see. So I have to emphasize and show you that it's a scalar. Now, if you have a scalar multiplied by a, like twice a, you multiply it by 2, you extend it by 2 as a factor, and you keep the same direction. That's what's happening here. It's gonna give you the same thing as if you multiply the two vectors first, then multiply by a scalar. Or take the scalar to be first, then do the dot product. Any way you do it, it's gonna give you the same answer. Now when you say 0 times a, that's not right. This is 0 dot a. Okay, we're using dot product, which means this 0 is a 0 vector. So, for example, here, if this is a 0 vector, that's going to be 0, 0. If this is a 0 vector, you're not going to see even ijk. Like, we didn't see the I. So, if this is a 0 vector, multiply by this, are you going to multiply components and take your time? It's going to end up 0. And that's what this right here says. Now, we talked about the formula, multiplying the components and adding them. Let's talk about the other formula, which includes the angle in between the two vectors. If theta is the angle between the two vectors a and b, then the dot product between the vectors a and b will be the magnitude of a multiplied by the magnitude of b multiplied by cosine the angle in between. Sometimes we are interested in the angle, so we need to solve for cosine theta first by dividing both sides by those magnitudes. And this is what I mean. You don't have to memorize it, you could just take it from here if you want. Now, to summarize so far what we have on the dot product. If you have it components, the dot product will be as shows right here. If you have an angle in between, you have this. Now sometimes we use both at the same time, meaning to find the angle, maybe you will find the product from here, then you move on, which we're going to see in an example coming in a few minutes. So the dot product is called, or is, a scalar product. It's a constant. And sometimes instead of calling it dot product, you could call it inner product. Here's some interesting facts about this formula and advantages when you refer to this formula. I want to keep them all in one slide. That's at least my style. I like to stay focused when I come back to the video and look at it. I could see everything on one slide. Especially when I do problems, I don't know if you noticed, and if you're new here, you're going to notice that. If a problem takes a lot to work, I try my best to keep it all in one slide. Instead of like halfway, I clean up the page and start working, continuing with the problem. I never liked that before. So I like to see everything from the beginning till the end. These ones, because they are more than one piece of information, to distinguish and let you stay focused. As you can see, I'm trying to make a different look, and I have different colors just to distinguish. Okay, let's go back to the topic. If the angle is acute, that means it's less than pi over 2 and greater than 0. That means it lives in the first quadrant. Well, looking at this right here, that tells me that this is positive, and cosine theta in this case will be positive. So these two don't play anything with the sign, positive, negative. The sign comes from this guy. If the angle is acute, cosine theta is positive. If you remember from trig, going around the unit circle, the cosine is positive in the first quadrant and negative on the second quadrant. So positive, 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 that means everything is positive. That means the dot product is positive. Which means also, if somebody gives you a dot b equals 7.3, that means positive 7.3, you could just imagine or visualize that the two vectors are actually forming an angle that is acute. That's what you want to know. Something extra info if needed. Let's take care of other cases on the same slide. As I said, same slide. If it's obtuse, that means you are on the second quadrant. Well, cosine is going to be negative. As I mentioned earlier, these two will not affect, so the dot product will be negative. How about if it's in between, right angle? Cosine is going to be 0. The dot product is 0. So whenever if somebody says verify or test if these two vectors are perpendicular, all what you need to do is do the dot product, which doesn't take long to do. And if the dot product is 0, because this is 0, that means everything is 0, we say perpendicular. With vectors, we sometimes use the word orthogonal. So that's another way to test perpendicular. Keep that in mind, because you're going to use it for the homework and some other problems. Now, we talked about acute, we talked about perpendicular, and we talked about obtuse. First quadrant, second quadrant, right on the positive y-axis. Here's some special cases when they are both on the same direction or both opposite direction. Same direction, that means the angle between them is 0. Now, I don't want to graph this on top of this one. They don't have to be on top of each other to call it same direction. As long as they're going this way with, let's say, 0 angle or 15 degree. If this goes up with 15 degree and this goes up with 15 degree, they could be graphed some other places, not starting from 1. You don't have to start from 1 or 1, 3. They don't have to start from there. So that means the angle between them is 0. If the angle is 0, cosine is 1, which means the dot product is the magnitude of A times the magnitude of B. In case if they go opposite directions, that means cosine is cosine 180 degree or 100 pi, that's -1, so that's the difference. So when you have this positive, that means same direction. When you have this negative, magnitudes only with a negative sign, that means opposite directions. I think that's good enough for this slide. Let's move on. Here's an example about what I mentioned earlier. Find the angle between the vectors. Well, to find the angle, we know the formula, but we need the components or the ingredients for that formula. So this is my advice. You don't have to, but that's how I do it. Take a look. First, I find a magnitude, Pythagoras theorem, square root of a1 squared plus a2 squared plus a3 squared. I'm not reading the numbers because you could just follow me and see it. You find the magnitude of b, find the dot product between a and b. Now we're ready for the formula. This is the dot product, 2, and those are the magnitudes right here. Since we need theta, find the angle, I need to take cosine inverse of this much. Using a calculator, radian mode, I got 1.46 approximate. If you want to convert it to degree, it's about 83 point something or close to 84 degrees. I think that is clear, even though maybe I was going a little bit fast, but you could follow me on the steps. The concept is more clear and the idea is what I'm trying to focus on. Every time you want to stop the video, I mentioned that before, I'll keep saying it over and over. You could hit the space bar, that's like pause the video. If you hit the space bar again, it will play the video. So keep in mind, if you feel like I'm going too fast, you want to look at the numbers, you could stop the video anytime you want. This is now very interesting topic when you talk about vectors. Projections. When you project, this is a vector A and this is vector B. We're going from P to Q, and in short we call it vector A. P to R, in short it's called B. If I drop a perpendicular right here and I keep it from this point to this point, point P to point S, that is called a scalar projection. The books usually call it the component of B along A. Kind of like the shadow straight down of this vector on this vector, from this vector to this vector. Same right here, so I'm not going to read this again. The only difference is if the angle is going obtuse, your projection is going to be on the left. Alright, just keep that in mind if this is a second quadrant. Now, how do you make a projection like this, which is a scalar, a vector? This is what's coming after this right here. Before I move on, I want to emphasize from last video that this side inside a right triangle is my adjacent, and this is my hypotenuse. So cosine theta is the adjacent, which has a name for me now, over B. And if you do the cross multiply, you get the adjacent by itself. And the adjacent is the magnitude of B, which is the hypotenuse, the length of it, multiplied by cosine theta. I did that on the last video. So, going back to the dot formula, focusing on magnitude of B cosine theta, you could see I'm using the black color right here. To solve for this, I'm going to divide both sides by A magnitude, and now you have it. This is the formula for the scalar projection of vector B over or onto vector A. This is the summary of this slide. The scalar projection of B onto A will be written as comp B index A equals the magnitude of B cosine theta, or differently, A dot B divided by magnitude of A. Now, how do you make that scalar projection a vector? Like this. This is a vector, right? I'll give you two ways. You put an arrow here, you make it a vector. I'm just kidding. That's just like a joke. The right way is actually you multiply that scalar by a unit vector in this direction. You're saying to me in words, to make this as a vector, I'm gonna go this direction, this way, same line, same direction. Well, this has a direction. This is vector A. The unit vector of A is one unit here, keeping the direction. It's a vector. And that's the game. This is the scalar. If you multiply it by a unit vector of A, you are telling me I need this much to go that way. As simple as that. Hopefully I'm not confusing you. It's so simple. Just multiply your much. How much is that? That scalar thing. Times, let's say, 1i plus 2j, which is not true, because 1i plus 2j is not a unit vector. And that should do it. You gave it a direction. Not with the marker as I started. If you want to simplify this, you see that I have magnitude of A down twice. One earlier and one came from the unit vector. You could write them together. Keep this outside. That's another form. It doesn't hurt to know both. Alright, We're almost halfway. I'm looking at the slides. Find the scalar projection and the vector projection of P112 onto A, -2, 3, and 1. Well, we know the formulas, so I'm trying to find the components or the ingredients first. Let's do that. You know how to find the magnitude of A. The scalar projection is A dot B over A. To do the multiplication, it's kind of small to read here, but you know how to do it. 1 times -2, 1 times 3, and 2 times 1, and add them up. It's a 3. Over the magnitude of A, which was done on the side, square root of 14. Done. We're done. That's it. That is the scalar projection. Now, I want to make this as a vector. But in which direction? Direction of A. And that's how we do it. The vector projection is the scalar projection times the unit vector in the direction of A. So I multiply by a unit vector that comes from direction of A, which is A divided by its length, to shrink it down to a unit vector, but keep the I, J, K components valid to give it the direction of the vector A. So, doing the math, these came up to be the same. So that's going to be square root of 14 times square root of 14, which is just 14. I have 3 outside, and now I have this vector. Multiplying in, you could simplify more, like the 2 and the 14 will give you 1 and 7, as you could see. 3 times 1, negative stays, and 7 down. The rest, I'll leave it to you. Here's a very interesting topic as application to dot product and projections and vector calculus. One use of projections occurs in physics in calculating work. I have everything for you, so don't worry. And I'm going a little bit slow because I want you to follow me, not just like to keep stopping the video and read. The work done by a constant force, F. That's how we start with a constant force. Easier to start. In moving an object through a distance d is W for work equals F for force, d for displacement. But this applies only when the force is directed along the line of motion of the object. That's right. What about if it's not? Suppose that the constant force is a vector F, which is PR. So it's not going the same direction, pointing in some other direction as shown in the graph. And we're moving the point from P to Q, or we're moving the object from this point to this point. That's the distance or displacement. If the force moves the object from point P to point Q, then the displacement vector is D or PQ. That's right here. The work done by this force is defined to be the product of the component of the force along D and the distance moved. This is a scalar projection. Do you remember it? So you bring this down because that's what's going to affect. Multiply by by D magnitude, as it says right here. But look at this. Looks like the dot product, but rearranged. Why don't you take the D in next to the magnitude of F? That looks like magnitude of A times magnitude of B times cosine the angle between, which is a dot product. So now you have it. In case if you're not going the same direction, you have an angle between. The work is F dot D, where F was mentioned up. I don't want to read it again. And D was also mentioned. I don't want to read it again. So the work done by a constant force F is the dot product F dot D, where D is the displacement vector. Here's an example as an application. A wagon is pulled a distance of 100 meters. We're pulling this 100 meters, that's down here, along a horizontal path by a constant force of 70 newtons. The handle of the wagon is held at an angle of 35 degrees above the horizontal line. Find the work done by this force. W equals F dot D. So you're going to go F and D magnitudes times cosine 35. The magnitude of F is 70. The magnitude of D is 100. Cosine 35 with a calculator. We get 5734 Nm, newtons meters, or joule. Here's another example. A force is given by a vector F equals 3I plus 4J plus 5K and moves a particle from the point P, which is 210, to the point Q, which is 462. Find the work done. The displacement vector is from point P to point Q. We could do it by saying the following. Take a look. 4 minus 2, 2. 6 minus 1, 5. 2 minus 0, 2. Now we have D. The work done is F dot D. We know F, which is up here with the IJK, and we know D, which is a different form, the brackets form or the less than, greater than. So you could rewrite this the same way, so you don't have to get confused. 345 dot 252. 3 times 2, 4 times 5, and 5 times 2, and add them up. 36. If the unit of length is meters and the magnitude of the force is measured in newtons, then the work done is not just 36 without units next to it, will be 36 joules. I think that should do it. It's almost like half an hour. I tried my best not to make it over 30 minutes, and this is my plan. I will do my best not to make my videos over 30 minutes. I think less than 30 minutes, between 10 and 30 will be the best. Thank you for watching. I'll see you in the next one within 24 hours, hopefully. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.